Hello everyone. So today what I'm going to do is motivate, or try to motivate at least, the fundamentals of quantum mechanics and where it comes from really. So as Richard Feynman once said, and I'm paraphrasing when I say this, that at the heart of quantum mechanics is one experiment, and that experiment is Young's double-slit experiment, an experiment we commonly learn in school to understand and appreciate diffraction and interference patterns. Before we get into the double-slit experiment though, let's do a thought experiment that you see the setup here on the screen. So on the screen you have a gun, a conventional gun which fires bullets. Let's not get too violent here. Let's say these are plastic bullets. And bullets, as we know, are particles. They're lumpy things with definite shape, size, and mass, right? So we can roughly predict its behavior using conventional classical mechanics, right? Because they're lumpy, large objects. All right, here you have a kind of a block that has a hole in it. We call it a slit, right? And this slit is labeled 1. So that is the first slit that we are investigating in this experiment. And here, behind this slit, you have somewhere down distance this screen. Okay, so on this screen you can basically see where the bullet passes the screen and lands on this screen, and you basically see a pattern emerging, right? Basically holes made by the bullet or something like that. Okay, so what do you expect to see? Well, you're firing bullets through a hole, and you expect the some bullets will basically at least some bullets will basically cross the slit and go through the slit, and you will definitely see some kind of pattern emerging that is that will roughly be kind of like this, right? Kind of like this. So behind slit 1 you'll see largely a collection of bullets, this high density kind of pattern here that is basically telling you that most of the bullets that pass through the slit end up right behind the slit, right? That is understandable, while some may basically be deflected and collect somewhere to the sides, but nothing on this side or nothing down the middle, right? It's basically going to be most of the bullets are going to end up right behind the slit. Okay, so now let's do a certain modification to this, and let's see what's going to happen if we move the slit position from here to down there to the right of our block. So you fire the bullet again, and now most of the bullets that get through this block will pass through the slit. Understandable, that's not very hard to do, and they will pass through, and essentially you will see a collection of bullets or pattern on this side, basically right behind screen 2. And again, that is not very hard to see why that is the case. Well, you have bullets, lumpy things, particles, seeing a hole through which it passes, and most of them collect right behind the hole. Some may be deflected and collect very nearby the high density region. All right, so essentially what we have is a probability of bullets ending up in different regions on this screen, right? So if you were to say, okay, all of this, the vertical region, the vertical direction, let's use my pen here, all of the vertical region is basically the position of the bullet, and on the vertical axis I can basically plot a relative probability, that is where the bullet actually ends up. So if you were to draw a probability graph, basically count the number of bullets that end up in this region right here or end up on the screen, what you see is there is nothing on the right side, there is nothing in the middle, a lot of collection of bullets on the left, right? So if you were to draw a probability graph or a distribution of the bullets, you'll have something like this: a high density to the left of the screen, and as you go to the right, basically there is nothing, right? So again, we can do the same thing for the second experiment with the slit position changed. Let's just be lazy and paste my work here, and now the graph changes a little bit, and I want you to imagine, or I want to try it before you actually see what the graph looks like, and I guess I hope you can guess what the graph shape is going to be like, right? So you have nothing on the left in this screen, and most of the bullets end up on the left, on the right, sorry. So basically you have a mirror image of the graph that we had before. So all of the bullets basically end up on the right side of the screen. So let's call this P2 as a function of x, and let's call that P1 as a function of x. Sorry, I have to use a different color. Okay, so this is slit 1, this is slit 2, and now we go into the double slit experiment, which means we basically combine the two slits and we have this kind of a setup that you see now. So one slit, two slit, you're firing a bullet, and the bullet can either go through slit 1 or through slit 2. And you know what's going to happen because you know what happens individually. Basically, most of the bullets will either end up behind slit 1 or most of the bullets will either end up behind slit 2. Nothing in between, right? And you can obviously now guess what the pattern of the probability distribution will look like. Let me just again paste my previous graph here, and I want you to again guess or try to guess what kind of a graph it would be. Let me give you the answer. It's going to be an average of the two, right? Basically you take the two together, join them to make one single experiment, two slits, you end up with a distribution that looks like this. Basically a combination of the two will give you a normal distribution, right? So let's call this P of x, basically the total probability, and it's nothing but the summation of P1x plus P2x, right? So let me make this summation sign a little bit better. I hope that's better. All right, so now from elementary knowledge of statistics and probability, all of this looks very, very easy to understand. So let's zoom out and see and summarize what we have. We had one slit, most of the bullets ended up behind slit 1, and we had this kind of a graph. Basically most of the bullets end up on the left of the screen, and slit 2, when shifted to the right, basically most of the bullets end up to the right of the screen parallel to slit 2. And you combine the two slits to make into a double slit experiment with the same bullet pellet. The screen basically is a combination of the distributions of slit 1 and 2, right? So you get this kind of a probability graph. And from elementary knowledge of probability and statistics, well, this is not very surprising. Essentially what you have here is this probability distribution of bullets is going to be the average of the two slit 1 and slit 2 distributions. Okay, so far so good. Everything classical, everything makes sense, everything intuitive. So now the weirdness of quantum mechanics comes in when you have replaced the conventional gun with an electron gun, which essentially fires electrons at this double slit. And here on the screen, behind the screen, right behind the screen, you have basically placed a detector which makes a click kind of a noise every time it detects an electron that reaches the screen. We make sure that this electron gun has a low intensity, so as it fires only one electron every time it fires. And whenever an electron, whichever slit it gets through, if it gets through anyway and ends up on the screen, there's one click. All right, there may be times when there are no clicks, so that means there are no electrons actually passed through the slits and ended up here. And there are times that there is only one single click. That means one full electron reached the screen. So there is never any half click here and a half click here or a half click there, because of the fact that you're essentially treating again lumpy particles that we know, right? Electrons are lumpy things with mass. What we measure on the screen then is basically the relative probability that the electron passes from the gun through the slits to somewhere on the screen. Okay, and every time it gets to the screen there is a click and the detector moves to catch electrons. Now what would you expect to see? Well, as we established, we have made experiment very ideal in the sense that electrons are forced to be acting like lumpy particles like the bullets, and So what you would expect is basically the same result as the bullet. So some electrons get through hole 1, some electron gets through hole 2 or slit 2, whatever. And so you would expect most of the bullets, most of the electrons will end up to the basically parallel to slit 1 or parallel to slit 2 with nothing really in the in-between region, or nothing significant. So you would expect the probability distribution to resemble the Gaussian distribution or the normal distribution that we saw in the previous discussion with traditional bullets. But quantum mechanics is so weird that what you actually see is something like this. Say this should be a little bit lower, but okay, you get the point. Basically, you don't see what you expect. Okay, you don't get a normal distribution like you did before, but rather you get this weird kind of a shape. That means, okay, here the amplitude, or basically the probability of electrons reaching right on the edges of the screen, let's say here, are not zero. They have a maxima, and then you have a minima, and then you have a maximum again. Right? So essentially, this is what you would expect from traditional wave interference, right? So what does that mean? Well, I hope you have your school physics memories when I'm saying this. Well, if you replace the electron gun with, let's say, water waves will get through the slits, and essentially a wave pattern will emerge of two waves that are kind of, let's say, drawing things correctly, and let's use a blue marker here. Comes out of slit 2, and the two waves basically interfere, and in some regions they may interfere constructively, and some other regions they may interfere destructively, right? So when they have constructive interference, so you have a larger amplitude, so those correspond to the maxima, and when they interfere destructively, you have a least amplitude, which corresponds to a minima, right? So this is what you would expect from a wave-like thing. But we established from the start of the experiment that electrons are lumpy matter particles. So what happened? Well, that is what the weirdness of quantum mechanics is basically like. So de Broglie, I think a French physicist, he proposed this idea of matter waves. So basically, electrons, which are traditionally lumpy particles, have wave-like behavior, okay, and he called them matter waves. So what if you did this experiment with light? Let's say you replace the electron gun with some laser gun, okay, so basically shoots laser beams through the slits. So from Einstein's photoelectric effect, we know that light is made up of quantized particles that are called photons, right? So light is basically lumps of energy or lumps of quanta, which we call photon. And if we have a low intensity laser beam, which ensures that 1 photon per second is emitted, then you would see a very similar kind of a graph of probability distribution that you see here with the electron gun. So essentially what it means is electrons are kind of behaving like light. For light, if you remember your classical electricity and magnetism, you would say, okay, that's not so surprising for light because we know light is a wave traditionally. So this kind of an interference pattern for waves is understandable. But the conundrum is, electrons are particles. Why do they exhibit wave-like behavior? And how do they do it? All right. So whatever your case might be, you have now essentially established that the probability here, we are calling this now the probability. Let's use red just to avoid confusion. This probability P of x is no longer equal to P1 x plus P2 x. Remember what P1 x and P2 x are. P1 x would be the probability distribution emerging out of slit 1, and P2 would be the probability distribution of electrons emerging from slit 2. So those are no longer equal, because for slit 1 you would get a distribution that looks like, let's use white. So for C1 you get a distribution like this. For P2 you'd get a distribution that looks like this, and if you add the two you get a normal distribution, which of course isn't this one that you see. All right, so now we have conclusively proved that quantum mechanics does not really support our intuition. So the goal of physics is not really to be satisfied by conundrums or by confusions, right? So we have established, okay, the electrons sometimes behave as waves, but we know traditionally electrons are particles. So can we actually ensure which one is it, or at least try to? Well, we can try at least, right? So how do we try? Well, we do something that kind of is very basic. We want to see the electrons emerging. So you say, hold on, you can't really see electrons with the naked eye. Yes, but we can see light, and if we place a light just behind, let's say here we have a light source or something, and it emits light, right? And whenever electrons emerge from the slits, they interact with the light and essentially get scattered. So basically they collide with the light beam. So let's say an electron comes out of slit 1 and then the light beam that happens to interact with it collides with the electron, and the electron gets scattered off, or gets scattered to some point on the screen. Okay, so we see interaction with light. So then it is an attempt to see if individual electrons are kind of getting scattered by light waves or individual photons of the light, right? If we have electrons coming out of slit 2, then they will interact again with some photons that is emitted by the light source, and then get scattered by that as well. So if we see a scattering event, let's call it, if we see a scattering event near slit 1, then we know that electron came out of slit 1. If we see a scattering event near slit 2, then we know for sure the electron emerged out of slit 2. Then what would be the probability distributions? So then what we have is, this is the probability P1x, because anything emerging out of slit 1 is getting scattered near slit 1. So you get this kind of a graph. And then you have anything emerging out of slit 2, you get this kind of a graph. Let's call that P2x. Right? So most of the electrons either end up behind screen 1 or behind screen 2, as we are seeing it getting scattered by the light. Then what is the total probability? Well, then you're back to the case where your probability, the total probability, is nothing but the sum of the two P1x and P2x, and that is exactly experimentally what we observe. So essentially what the result of this experiment is, when you're placing a light source just behind the slit to observe the electrons coming out of the slits, the probability distribution is resembling what we had with the traditional bullets coming out of the traditional gun. So you end up with, again, a normal distribution. All right, so this is the total probability, and that is exactly what we observe if we place a light source just behind the screen. Now hold on a minute, where did this interference pattern go? When we are not seeing the electrons, they seem to behave as waves, displaying interference patterns. But when we actually observe the electrons with this light, as light scatters the electrons, we see electrons are behaving as lumpy things like the bullets. Well, I hope you appreciate how weird quantum mechanics is. This is what we call the observer effect. So when you observe a particle, it essentially behaves like a particle, or it is forced to behave like a particle because we are observing it. When you're not observing a particle, and we're talking about extremely small scales here, not bullets, we're talking about atomic scales or lower, like electron scales, they tend to behave as waves. And just the act of observing destroys the interference pattern. Well, this idea is ingrained in the Heisenberg uncertainty principle, or just Heisenberg's uncertainty. Concretely, Heisenberg tells us that there is an uncertainty in measurements of the position multiplied by an uncertainty in measuring the momentum p, and that this product will always be greater than approximately equal to some factor of h bar. H bar is an extremely small number, so quantum mechanics is essentially ruled by this constant h bar, which is known as the reduced Planck constant, or just Planck constant at this point for brevity. So for classical mechanics, in every kind of classical events, we never talk about h bar, so h bar is set to 0. H bar is important, that is at small scales of nature. We have quantum effects, we have the Heisenberg's uncertainty principle, and this tells me that if you want to determine position very precisely, and that is exactly what we were trying to do in our experiments above, we were trying to determine the position of the electron, it automatically increases the uncertainty in measuring the momentum. So we are locating the electrons very precisely. We're saying that we're seeing the electrons being scattered off near slit 1, and we are determining for a fact that the electron emerged out of slit 1. However, this interaction between the photon and the electron gave it an uncertainty in the momentum, and that is the most fundamental result of quantum mechanics. You cannot measure the position and momentum simultaneously, so a precision in one measurement introduces automatically indeterminacy of the other quantity. But there is a valid question that you can ask, that is, can we use a weaker source of light? Can we weaken the light and basically lessen the effect? That is, can we recover the interference pattern if we just use a weaker source of light? Our friend Einstein told us that light is quantized. Light is quantized, and it has energy that is determined by its frequency. So h times f. H is the Planck constant. H bar and h are related by a factor of 2 pi, which is not important at this point. And weaker source of light means lower energy. Low energy means weak. And low energy then entails low frequency. That means lesser number of photons. But that just means that sometimes when electrons are emerging out of either slit 1 or 2, we miss seeing them. All right, we don't really see them. So if we don't see electrons, we get the interference pattern. If we do see electrons, we get this normal distribution. So what does that mean? Well, it means that sometimes you'll see interference, sometimes you'll see this normal distribution, and if you have a weak source of light, then you may see kind of a averaging between these two distributions. That's all. That's the best you can do, but that doesn't really reduce the indeterminacy of the electrons behaving as waves or particles. Okay, so another thing you can ask is, now, can you use light of longer wavelength? Well, longer wavelength, remember how f and lambda are related for light. So c equals f lambda. C is the speed of light. So then lambda is c over f. So if you have a longer wavelength of light, then you have a smaller frequency of light. So that means, again, smaller quantity of photons. However, there is another relation that is of importance here, that is coming from de Broglie's matter wave interpretation of light and electrons as well. So if you're treating light as particles, photons, that which we are in this case, then de Broglie tells me that the wavelength of photon is equal to h, the Planck constant, over its momentum p. Okay, so then if you have a longer wavelength, that reduces the momentum. So essentially what you're doing here is, if you use longer wavelength, you're kind of making the momentum precise. But what would that do? That would make the position indeterminate. That will introduce more uncertainty in delta x. And what does that mean? Well, that means that if you have too long of a wavelength of light, and light scatters the electrons coming out of one or two, if the wavelength of light is greater than the slit separation, how far these slits are, then you don't really know out of what slit the electrons are emerging. So you have lost the precision in position. So there is a limit to how big of a wavelength you can use. This wavelength cannot be longer than the separation of the slits, because if it is, then you're back to the same problem. You don't know out of which slit the electrons are emerging from. I want to summarize two things in conclusion. Essentially, what we have seen is, at atomic scales, our intuition fails, and the quantum nature of the world becomes apparent. Things are quantum. And another thing that I hope you realize, that probabilities are very important. And what we used to find in classical mechanics, in classical kinematics, is the position of the particle is no longer as obvious. What we now have is probability amplitudes. Probability amplitude. And these determine the location of particles. And what are probability amplitudes would be the subject of a future video if you're interested. Thank you.